Welcome students. Today we want to discuss about linear Diophantine equations. So consider the following motivational problem. Vijay wants to buy a face mask and hand gloves for his family. The cost of each face mask is $57 and cost of each hand gloves is $22. He has $400 and he wants to spend it all. How many face masks and hand gloves can he buy? So in this case, let X be number of face masks and let Y be number of hand gloves he can buy. So if you multiply 57 times X and 22 times Y, this should add up to $400. Now note that we do not want half a face mask. So we are interested in only integer solutions of this. So X and Y are integers. And not only that, we want X and Y as a positive integer solution if it exists. So such equation is called Diophantine equation. So what is a Diophantine equation? So Diophantine equation is an equation where you require the solutions to be integers. Equation for which you need equation with integer solutions. So you want to only solve for integer solutions. One known example is say x squared plus y squared equals to z squared. Your Pythagoras theorem when you're looking for a triangle with integer sides, a right angle triangle. That is an example of a Diophantine equation. If you're looking for solutions for this in set of integers, it can be positive and negative both, right? But in our special motivational problem, we are only interested in positive integers. Yeah, there's no concept of negative gloves. So what is a linear Diophantine equation? So Diophantine equation which is linear is called linear Diophantine equation. In particular, a linear Diophantine equation in two variables can take form ax plus by equals to c. Since you have two variables x and y, it's a Diophantine equation in two variables. And it's linear because the powers of x and y both are 1. And you can see that you have ax plus by equals to c. You're looking for x and y, even though they are unknown, you're looking for the solutions in Z. And a, b, c are some integer constants. So now once you're given this Diophantine equation, you want to ask the following question. So does given Diophantine equation has an integral solution? And the answer is not yes all the time. We can construct one example quickly where this will not happen. So suppose you take 2x plus 2y equals to 1. This will have no integer solutions. Why? Because left-hand side, this is even. This is even. If you add two even numbers, you get even. So you can't get equals to odd, right? So this Diophantine equation has no solution. Now, how about Diophantine equation, linear Diophantine equation in general? And if the solutions exist, how many of them exist? So that is given by the following theorem. So let AB be non-zero integers with D equals to AB, where D equals to AB means D is the GCD of AB. Then the equation AX plus BY equals to C has no integral solutions, means it has no solutions which are integer if D does not divide C. Okay. And if D divides C, then the solutions are, there's not just one solution, there's infinitely many integral solutions. And not only that, the integral solutions are a form. So if you give a particular solution, x equals to x naught, y equals to y naught, one solution, from there you can construct all the solution by saying x equals to x naught plus b by dn, y equals to y naught minus a by d by n. So let's prove these theorems. So proof for the first one, A. So suppose or if ax plus by equals to c has a solution, implies there exists, say, alpha and beta belonging to z, such that a alpha plus b beta equals to c. Right? Now note that D is the GCD of A and B. This implies D divides A and D divides B, but this implies D divides any linear combination of A and B. That would mean that D divides A alpha plus B beta, which means D divides C. Yeah, so if the solution exists, then D divides C. So by contrapositive, if D does not divide C, then ax plus by equals to c has no solutions, no integral solutions. Of course, otherwise it will have solutions, right? Because it's a line in R2 if you're considering non-integral solutions. But our goal is to only consider the integral solutions. Okay, so clearly if D does not divide C, then there are no integral solutions. Now, how do you basically see this geometrically? So geometrically, if you want to consider this, consider the following line. You have 2x plus 4y equals to 5. Here GCD of 2 and 4 is 2, and 2 does not divide 5. So no integral solution. Now, what does it mean geometrically? So what are the possible solutions, integral solutions to any linear Diophantine equation? The solutions will be lying here, right? These are the points where x and y both are integers. So these are the lattice points, so-called lattice points. Now, if you see 2x plus 4y equals to 5, this equation, the graph of this equation misses the lattice points. Yeah, so it will never cross a lattice point, so no solution. So it does not passes through lattice point. So no solutions. So no integer solutions. Okay. Now the second case is, so if D divides C, then there are infinitely many solutions. All right. So let's try to show that there are infinitely many solutions. And not only that, so it's basically saying two things really. Then there are infinitely many solutions. And these solutions are of form x equals to x naught plus b by dn, y equals to y naught minus a by dn for all n belonging to z. And all the solutions are of this form. So it means two things. It means that these representations, these numbers are the solutions, and all the solutions look like this. So let's prove that. So B, so if D divides C implies there exists K belonging to Z such that dk equals to C, right? Now, D is GCD of A and B. This implies there exist two integers, let's say M and N belonging to Z, such that AM plus BN equals to D. Yeah. So existence is already, there already exists integer M and N such that AM plus Bn equals to D. You can call this as Bezo's theorem, consequence of Bezo's theorem. Now what do we get? So multiply throughout by K. So this means A M K plus B N K equals to dk, which gives me, this is C, right? So if you call x naught and y naught, which is m by k, y naught is n by k. They both belong to Z because they are multiples of integers. A product of two integers is an integer, is such that ax naught plus by naught equals to C. So you have produced, so we have produced, so what is the upshot of this? We have produced a particular solution. Now we want to show the second part. So for second part, we'll show it in two steps or two parts. Claim 1, x equals to x naught plus b by d n, and y equals to y naught plus b by n for all n belonging to Z are solutions to given LDE, so linear differential equation. So sorry, linear Diophantine equation, my bad, to given ax plus by equals to C. Linear Diophantine equation to given linear Diophantine equation. So let's start by substituting these guys. How do you check? You basically start with the left-hand side. You have a x naught plus b by dn plus b y naught plus b by dn. Sorry, this one has to be plus and the other one has to be minus. Which one? It doesn't matter. So what do we have? We have, again, here we should have taken a. Otherwise, they won't cancel, right? So one of them is plus and the other one is minus. So let's check if these are the solutions. So if you multiply it out, you get ax naught plus b by dn times a plus by naught minus b a d divided by d times n. So these guys will cancel out and you get ax naught plus by naught. But that is C because x naught and y naught, since x naught and y naught are particular solutions, right? Are particular solutions. Particular solutions. Therefore, we get that these are the, so these are the solutions. So therefore, these are the solutions. Now claim 2, all solutions are of form x minus x equals to x naught plus b d by n, and y equals to y naught minus a by dn. So all solutions are of this form. For what? For linear Diophantine equation, ax plus by equals to c. So how do we prove that? So we get what? We have ax plus by equals to c. Since x and y are solutions, Again, when we talk about solutions, we say they are basically integers. And similarly, you have given this, since x naught and y naught are particular solution, are still solutions, right? Particular solution. So if you subtract these two, you get a times x minus x naught equals to, I'll bring it on the other side, minus b times y minus y naught. But what do we have? We have GCD of, so we can divide both sides by the GCD. GCD of a and b is d. So we have a by d times x minus x naught equals to minus b by d times y minus y naught. Now note that this is a defined integer, because this is an integer, this is also an integer, right? So since GCD of a by d and b by d is 1, that means what? That means a by d divides minus of y minus y naught, or divides y naught minus y. This would mean there exists an integer n belonging to z, such that, what do we get? We get a by dn equals to y naught minus y. This would mean that y equals to a by d y naught minus a by d n. Similarly, you can argue, or you can basically put this y value back in this equation. You will get a times x minus x naught equals to b a divided by d times n, and you divide on, so you get d squared by d, and then when you bring it on the other side, you get x equals to, cancel out a by d from both sides, you get x equals to x naught plus b by d times n. So you have shown two things, not only that these are the solutions, and all the solutions also look like the following form. Now, let's try to see geometrically, how does it looks like? What is the story? So here GCD of 2 and 3 is 1. So that would mean that, and 1 divides 1, right, which is your C. Your C is 1. Therefore, there are infinitely many solutions. So let's take an example here. So you can see, if you take 2x plus 3y equals to 1, if you look at this lattice point, this is a solution. If you look at this lattice point, this is also a solution, right? So solution 1. So what is the particular solution here? The particular solution is x is 7, y is minus 4. Now, to this solution, we can make it as what? We can make it from one solution, we can get to the other solution. Let's see how. So what will be the other solution? So other solutions are of form 7 times. So I'm going to write from here, x is 7 plus b by d. What is my b? My b is 3 by d. D is 1 times k. Similarly, my y is what? Y is minus 4, because minus 4 is a particular solution, plus, sorry, y is comes with a minus sign. So minus a by d, minus a, which is 2, by d, which is 1, times integer k, or n, if you want to call it n. Let's just call it n, n. So the solutions are of form x equals to 7 plus 3n, and y equals to minus 4 minus 2n. So now let's see. So if you take n to be minus 1, what do you get? X equals to what? X equals to 4 and y equals to minus 4 plus, so we get y equals to, sorry, if x is so 7, so I got 7 plus 7 minus 3, which is 4, and y is going to be minus 4 plus 2, which is going to be 2. So I will hop from here to the next solution by going up 2 units for y, and then going right by 2 units. Then again, I can go to the next solution by hopping up 2 units and going right by 3 units. Again, I can go up 2 units and right by 3 units. Up 2 units, right 3 units. So this is how you can transfer through all the solution on lattice. So now let's try to solve this problem. So I had 57x plus 22y equals to 400. Now note that GCD of 57 and 22 is 1, and that divides 400. Yeah, is 1, and 1 divides 400. Therefore, there are how many? Infinitely many solutions, right? Infinitely many what solutions? Integer solutions. Of course, we are looking for special where x and y both are positive. So how do you go about it? So first you write the extended Euclidean algorithm. So you have 57 equals to 22 times 2 plus 13. This gives me 22 equals to 13 times 1 plus 9. Then I get 13 equals to 9 times 1 plus 4. And then we get 9 equals to 4 times 2 plus 1. And then finally we get 4 equals to 4 times 1 plus 0. So now let's rewrite this back. So this gives us 1 equals to 9 minus 4 by 2. So now I'll replace 4. So what do I get? In this case, I will get 1, this is equal to 9 minus, instead of 4, I'm going to write 13 minus 9 times 2, which is going to be 3 times 9 minus 2 times 13. Then I'll replace back 9 as 22 minus 13. So 22 minus 13 is 9. So 3 times that minus 2 times 13. This will give me 3 times 22 minus, so 3 times this, minus, so 5 times 13, and then this gives me 3 times 32. I will going to replace 13 now. 5 times 57 minus 2 times 22, or 22 times. So now when I multiply it out, I get 3 minus, so 10, so plus 10, so 13 times 22. So 13 times 22 plus 57 times minus 5. Okay, I should write this, the other thing in the bracket. So 22 times 13. So here we get what? So here I get 1 equals to, therefore 1 equals to 57 times minus 5 plus 22 times 13. Now, what do we get? So multiply throughout by 400, you'll get 400 equals to 57 times minus 5 times 400 is going to be 2000 plus 22 times 13 times 400 is going to be 13 times 4 is 52, so 5200. Now, this is your A, this is your X naught, this is your B, this is your Y naught. Now, what are the other solutions? So the other solutions are X equals to X naught plus B by D times K, and Y equals to Y naught minus A by D times K. So now here you have, this is same as minus 2000. What is my B? My B is 22. So 22 by D. D is 1 times K. And we get Y equals to 52 minus A, which is 57, by D is 1 times K. So now we want to make basically, so this is a solution. So for all K in Z, this is a solution to the Diophantine equation here. But we want a special kind. We want X and Y both to be positive. So let's see if such a thing is possible. So we'll see, let's see what 22, what K, what multiple of 22 will make this positive. So you can see roughly, I'll do a calculation here. So K is basically, so K roughly equals to, by 22, will make it around 0. So this turns out to be 90.6. So take K equals to 91 and check. So we get K equals to 91. We get X equals to minus 2000 plus 22 times 91, which is going to be 2, and Y equals to minus 57 times 91. That turns out to be, so that turns out to be 13. So X equals to 2 and Y equals to 13 are the required solutions. So how many hand masks? So sorry, face mask is X is 2, so 2 face masks and 13 hand gloves will be the required one. Now, are there more solutions? And the answer is no. You should increase the value and check that it will already overshoot 400. So this is the idea. So now, so the theorem can be generalized. So if n is greater than or equal to 2, if a1, a2, an are non-zero integers, then a1, x1, dot, 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 an, xn equals to c has integer solutions if and only if d divides c, where d is GCD of a1, a2, an. And moreover, same way, if there's one solution, you can construct infinitely many solutions. All right. So this homework, this is a proof, is a homework, or we can discuss this in the office hours. Now, these are the few problems. Right. Now, there is another connection I want to build with the linear algebra. So you have already seen that. So let me write down this thing. So ax plus by equals to c. So this can be seen as a system of differential equation, sorry, system of linear equations. Actually, there's only one. So let's say A, B, this is your matrix M or A, and you're solving X, let's call this as X, equals to B. Well, this B is already used, so let's call this as B. So this, when you multiply, you get C, you get B. Okay. So now what you do is the following. So how do you find out all the solution to this system of linear equations? You basically take X naught, Y naught, or rather X naught, Y naught. Let's call this as capital X naught is a particular solution. Then what are all the solutions given by? So what you do is the following. So, and X, well, bar be a homogeneous or solution to the homogeneous linear setup, linear equation system. So in this case, what is the homogeneous part? So you have X equals to 0. Then all solutions are given by X naught plus X bar. Yeah. And you see that if you look at X, so if you want to compute A, B times XY, so for the homogeneous part, you want to solve this, you can clearly see you'll get AX plus BY equals to 0. This would mean X equals to minus B by A Y, right? And Y equals to what you get. Y equals to, then you can substitute this to get your solution for Y. So Y you can take to be. So in particular, the better solution comes when you take one of the solution to this is the GCD, right? So yeah, you can work it out from there. All right. So you can construct all the solution as basically X naught plus X bar. So you can clearly show that these equation has solution. So what is the solution to this? So X is going to be, in this case, X is going to be clearly in this case, but B may not, if you have X equals to minus B by A, so this solution does not exist in this case, right? Because what if B by A is not an integer, right? So this happens. So what you need is that GCD of A and B. If this is D, then you will see that the solutions are given of form X equals to B by dk and Y equals to minus A by dk. So this is a solution, all right? So how do you see about it? If you substitute this in this equation here, you will see that this works. Okay, so this is a homogeneous solution to this equation. Now what you do is the following. So your x bar, which is a set of homogeneous solution, is given by b by dk minus a by dk, where k belongs to c. These are a set of all homogeneous solutions, and then you add that to the particular solution. Adding it to particular solution gives you, in that case, you get what? X0 plus x bar is going to be x naught plus b by dk, and y naught minus a by dk. You get all the solutions that way. All right, so that's about it. We'll do Diophantine equations in 3 variables in the office hours. Thank you for your attention.